Absolute value can be modeled by functions. This is our original function, y equals f of x. The first absolute value transformation is y equals the absolute value of f of x. You can think of this as a vertical transformation because all y values of the graph must be positive. Begin drawing this graph by first drawing all y values which are already positive on the original graph. Now that we have drawn all y values that are originally positive on the graph, we must make all other y values positive. To do this, take any negative y values from the original graph and draw them on the new graph with positive y values. Make sure you don't forget any y values on your original graph. Now we can see our final graph. The parts of the original are drawn in red, and anything that was changed from the original has been drawn in green. For the following graph, we are transforming the inner x values. You can think of this as a horizontal shift. Begin by drawing any values from the original graph on the right side of the y-axis. Now, you need to reflect all y values from the right side of the axis to the left side of the y-axis. Make sure to leave all original values on the graph. In this, we see that all positive y values from positive x values have been transformed to the other side of the graph. The final x value transformation is a combination of the previous graphs. Begin with the inner graph first. To do this, copy anything from your original graph onto the new graph. Now, make sure that all y values are positive to align with the entire function being positive. Since in this graph all y values are already positive, there is no need for another step. This might not always be the case. If there are any negative y values, be sure to make them positive at this point in time. We now move on to y transformations. To begin, look at your original function. For the following function, absolute value of y equals f of x, you need to make sure that all y values, when they are taken to their absolute value, match up with their corresponding y values in the original function. To do this, first draw all positive y values from your original graph. This includes anything that y value is 0. Next, reflect all of these positive y values over the x-axis and leave your original graph in place as well. The way you know that you've drawn your graph correctly is if you take any y value from any point on your new graph and find the absolute value of it, it should correspond to its value on the original graph. For example, at 2, the y value is negative 2. The absolute value of negative 2 is 2. And if we notice on our original graph, at the x value of 2, the y value indeed equals positive 2. Our final one is going to be a combination of x and y absolute value transformations. Begin with the inside of the graph. For this, we can look at our x value transformation from before. To do this, make your x value transformation. Now, make your y value transformation by reflecting all values over the axis. Since all these values are already positive, there is no need to alter your graph. Any other absolute value transformations can be found by combining all previous principles. Here are some easy visual ways to remember the absolute value transformations. Make all negative y values positive. Take all y values on the right side of the y-axis and reflect them over the y-axis. Take all y values above the x-axis and reflect them over the x-axis. We will now talk about limits. Limits are expressed like this. The limit of a function over x as x approaches a equals y. The approaching values can be written in three different ways. If a or your value is written with a negative sign, it means approach the value from the left. If a is written with a positive sign, approach your value from the right. And if a is written without a sign, approach a from both sides.
So, as the function approaches infinity, we can see that it follows the end behavior, which in this case is 0. As the function also approaches negative infinity, the limit is 2 because it is hitting the horizontal asymptote. As the function approaches positive 2, which is the vertical asymptote for this function, from the left, because it's negative, it is going down, which can also be considered negative infinity. But because negative infinity does not have a certain value, it can also be considered does not exist. As the function approaches 2 from the right, it goes up to positive infinity, which can also be considered does not exist because it does not hit a certain value. As the function approaches 2 from both directions, it goes in two different directions, which means that the limit does not exist.
Next, we will discuss what limits do as a graph approaches a whole. Our first example is x approaching negative 2 from either direction. We can see that in this graph, when x approaches negative 2, there is a hole. So the entire function must approach the y value of the hole, which in this case is 1. As x approaches negative 2, the hole, from the left side indicated by this negative sign, we notice that the y value is approaching 1. The same applies when the hole is approached from the right side. The y value is always approaching 1 because this is where the graph is headed.
We will begin by talking about the vertical asymptote and its limits for this function. As the function approaches negative 3, right here, from both directions, it goes down, which means that you would think it'd be negative infinity. However, the two lines do not have the same slope, which means that the limit does not exist. If this function approaches negative 3 from the left, as we can see, it goes down, which means that the limit is negative infinity or does not exist. As the function approaches negative 3 from the right, it also goes down, which once again means that the limit is negative infinity or does not exist. As the function approaches 1, right here, we can see that the y value approaches negative 2 from both directions. As the function approaches negative 1, right here, we can see that from the left, we can see that it approaches the y value of 1. However, if we look at the function approaching negative 1 from the right, we can see that it approaches the y value of 4. Therefore, when the function is approached when the function approaches -1 from both directions, there is no limit because there are two different y values. So a couple of ways in which we can determine the limit of certain functions when approaching infinity or negative infinity is by looking at their degrees of the denominator and the numerator. In this case, we can see that the denominator has a larger degree, which means that as x approaches infinity or negative infinity, the limit will always be 0. Next, if we look at functions with the same degrees on the top and bottom, we can see that it's the same. We can see that we just divide the coefficients, because as x approaches infinity and negative infinity, there will be the same asymptote. If the degree of the numerator is larger than the degree of the denominator, which, as we can see, x squared is greater than x, the process of long division will enable us to find the asymptote for both approaching infinity and negative infinity.